Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering, module number 2, that is Vapor Power Systems, part 3. So, in this lecture, we are going to focus on the important component of a steam power systems, that is steam generator, and mainly we will talk about fossil fuel type steam generator, for which the energy is supplied through fossil fuel. When this energy is supplied to the fuel, the water receives heat from the fuel, and that happens in a component what we call as a water tube boilers. Many a times we also talk about like modern steam power systems call it as a steam drum. So, we will try to focus on these two main important segments. Then we will also discuss about the how water is circulated in the boilers, which means that in a steam generator continuously we are supplying water, at the same time we are generating superheated steam. Sometimes the water is at saturated state, sometimes the water is also in the superheated state. So, to analyze this we need to see that how water circulation takes place. So, mainly because one is at gas phase, other is in the liquid phase. So, the density difference that occurs between gas phase and liquid phase has an advantage that makes us the circulation of water in the boiler. Another category of water boiler is the once through boiler, which means that when you supply heat to the water, the traditional way of going to superheated steam is through the liquid to gas phase and through latent heat of heat addition, and subsequently we go to the superheated state. So, basically we deal with the property diagram of pure substance for water that considers the dome. Now, in a once through boiler what happens, if you want to bypass the saturation regions, then liquid phase can be converted to gas phase. In other words, we can take water to steam directly, and such a boiler is known as once through boiler. That means, without going through the latent heat phase, we can go from water to gas phase directly. So, this is the overall discussion as of today. So, if you look at our previous analysis, when you dealt with what a steam power system look like, basically it has main three segments M, N, O and P. M stands for the supply of energy to the working fluid. So, our working fluid is water, and the supply of energy we can have it through fossil fuel, nuclear, solar, geothermal. So, many resources of energy we can use it. So, our main focal point of the few lectures from now will be on steam generators, and mainly we will be talking about the part M part, and in our previous lectures we covered turbines, we also covered condensers, and subsequently in other phases also we will cover the cooling towers. And additionally, if you look specifically for the Rankine cycles, the heat addition phase starts from point 4 and ends with the point 1 dash. So, from 4 to A, maybe heat addition phase starts from 4 to A is in the liquid phase. So, it is a constant pressure line. So, at constant pressure we keep on adding heat till we get the saturation point. Then from A to 1 is the latent heat of heat additions, that means liquid of water gets to saturated vapor, and from 1 to 1 dash it is the superheated region. So, that is the superheated steam. So, essentially speaking, from 4 to 1 dash entire things heat addition takes place into as Q in. So, that is all about the boiler does, but this heat addition phase in reality happens from liquid state to superheated state. So, this is essentially integral of various components, and all these components are part of this domain, that is steam generator. So, whatever I have explained so far, if you can recall them, they are like this. So, in power stations that operates mainly fossil fuel and nuclear fuel, the steam generators is the integral part, because their main aim is to produce the steam at a desired rate by burning the fuel in its furnace. And steam generator represent greater source of energy for the power plants, and they invariably use Rankine cycle. Now, for most of the modern power plants, when they are used as a steam generator, they operate close to 240 bar, which is mainly for superheated steam, and 70 bar for saturated steam. And if you look at the wide range of operations, that is from liquid to superheated regions. So, steam generator involves the complex combinations of the components, and they are mainly heat exchangers. They are known as economizer, boiler, superheater, reheater and air preheater. So, we will try to see how they are organized in a particular steam generator unit. Apart from this, there are auxiliary units like pulverizers, then burners, then fans, then we have ash handling equipments and so on. Now onwards, another important significance difference that we have been using is the boiler. So, essentially boiler is the word that is used in the Rankine cycle when you are handling saturated steam. That means, when we are going from point A to 1, whatever heat that gets added, that is latent heat of water, latent heat of vaporization for the water. So, when this heat is added, and that part of the steam generator component is regarded as a boiler. But a more precise or wide range of operations, we use the word called as steam drum. So, we look at the steam drum in very closely in the subsequent slides. So, let us talk about the steam generator that are used in the modern steam power systems. So, if you look at, I mentioned that the steam drum is the most generic word. So, if you look at the steam drum, it is like a cylindrical structure of certain diameter and length. And this steam generator has lot of tubes. So, they are called as a riser or downcomer. So, the word downcomer, actually the steam drum collects the water. I mean, it is a kind of a water reservoir for the plant. So, when this water gets stored in the drum, then what happens is that the buoyancy is taken as advantage. That means, water gets circulated or comes down through through some pipes which we call as a downcomer, and when it comes, it interacts with a header which connects this water with respect to fuel air systems. So, basically heat is added through this process. So, when this heat added, steam gets generated, and this steam passes through the another set of water tubes, and we call them as a risers. So, there may be number of downcomers and number of tubes which are used for risers. So, why you say riser? Because steam when its density comes down, it goes up, and finally, when the steam is again stored here in the steam drum, and then for subsequent transmission to next unit. So, basically the steam drum supplies saturated steam. Now, to get superheated steam, we have superheaters, which are another unit of entire water steam generating systems. We have superheaters, and some cases we want the steam to be reheated. I mean reheating of the steam, that means after it comes from the high pressure turbine, it again passes through the low pressure turbine. So, some reheating segment we used to do. So, there is a reheater, and apart from these are the major two units that is operated when we are covering in the beyond the saturated dome. Now, some of the units like economizer is another unit which is actually the word economizer essentially specifies that economically how you are using the energy which is used which is nothing but a exhaust, and how you are going to use them for initial preheating purposes. So, economizer does some of this initial preheating stuffs. Again, we also require the air to be preheated. So, that preheating concept also integrated with a what we call as air preheaters. So, basically wherever heat addition or heating is required for different parts of the power plants, that essentially is integrated with this steam generator, and ultimately entire energy that comes from the fuel air combustions, and here the fuel is mainly fossil fuel. So, this is about the overall concept of this steam generator, which is replicated in this diagram. So, now coming back to the classifications, there are three main segments of classifications. One is the utility steam generator, second category is industrial steam generator, and third one is marine steam generator. Out of these three, if you look at marine steam generator, they are mainly used for giving necessary powers for ships for marine applications, and that mainly use the fuel oil as a main source of heat, but again that is localized with respect to marine systems. Other is industrial steam generator. Normally it is also a kind of a power plant systems which is integrated with various auxiliary units like waste heat systems, which is again can be integrated with some gas turbine systems. So, they are like intermediate units that operates relatively low pressure at low pressures. But one important thing is that utility steam generator, this utility steam generator mainly used for thermal power systems, and they use two types of units. One is subcritical unit, other is supercritical unit. Now, while talking about subcritical unit, we use a water tube drum type steam generator, which I have explained earlier. So, in the subcritical unit, what happens if you look at this particular figure, that means we are operating the steam, that means from point 6 to 1 if you want to go, there are two paths. One is we have to cross this dome and go up, that means initially liquid water gets heat, that means from liquids to saturated liquid, then saturated liquid to saturated vapor, then saturated vapor to again superheated regions. So, essentially we are crossing this to reach point 1, our main path is covering this dome. That is what we call as subcritical unit, or which uses water tube drum type generator. Now, other type of generator, suppose you want to bypass this dome, then from 6 to 1 we can reach through directly without entering into the dome. So, that is possible if you operate your boiler at a pressure which is much above this critical point. So, this point in this dome, that is a one peak point which is called as a critical point for water, and this that means one should operate at the critical point, operate the boiler or generator at a pressure which is above this critical point, and that is what we call as a supercritical boiler or generator, and we call this as a once through boiler. Now, when talking about supercritical unit boiler, they operate at about 240 bar, just higher than the critical pressures. When the subcritical units, they operate either at 130 or in the range of 130 to 180 bar, and for which the maximum temperature falls in the range of 550 to 600 degree centigrades. Now, while operating these units, we try to get the power in the range of 125 to 1300 megawatt, and that for which the steam consumption is about 125 to 1250 kg per seconds. And for all these things we are using the energy from the coal to produce this power. So, these are the rough numbers that typically a steam generator that operates. Now, we will move on to component wise these things, and regarding industrial steam generator I have already mentioned. They operate with various segments of energy resources, either from coal, oil, natural gas, municipal waste, process waste, byproducts. So, it is a combination of all of them. So, that is the reason they call that as a industrial steam generator. So, they have flexibility of operating with multiple energy resources, but they since they have to operate with multiple energy resources. So, pressure range is relatively less and typically around 100 to 105 bar with a steam capacity of 125 kg per second. The last category, which is a low unit, so that is marine steam generators. They use main resources as oil, energy resources oil, and the superheated steam they produce at around 60 to 65 bar at temperature of 540 degree centigrade. So, these are the overall summary that what the steam generators normally operate. Now, we will move on to mainly the fossil fuel type generators, and they are essentially divided into the following components, like we call it them as a fire tube boiler, water tube boiler, natural circulation boiler, controlled circulation boiler, once through boiler, subcritical and supercritical type boiler. So, essentially the two broad ones are there, one is water tube type, other is once through type, and out of these two the natural circulation with that all these two either they can be natural circulations or they can be controlled way of circulation. They can be also subcritical, but once through boiler has to be supercritical. But the fire tube boiler is a very old concept. Initially when the concept of steam addition process starts, they started with the fire tube boiler. So, this is the overall summary. Now, we will start one by one just to give some introduction about the type of fossil fuel generator, and first category is the fire tube boilers. So, this concept was started from 18th century. So, here the concept was that we will have because it is a fire tube, the word stands for fire. So, we used to create some kind of fire in a tube. So, that is what it is, fire tube. So, there is a lot of coal stack, and through these coal stacks when you add just to burn this coal, so you will generate a flue gas that passes through a tube, and this tube is integrated with a cell with that circulates in which water comes in and water goes out. So, through this process water enters and we get the steam out, and exhaust of the flue gas goes out through a chimney. Now, here main important concern is about that we are not able to effectively utilize this fuel properly, because there are many waste we cannot control them. And second thing, here we can the main limitation for this boiler, it is it can produce the steam only up to 18 bar and with an efficiency of 70%. So, basically people started thinking of the subsequent innovations against this fire tube boilers, and new designs come up. So, that new design come up means instead of using the coal directly, the concept of fluid light bed boiler comes into pictures. So, those fluid light bed boiler schematically is shown here. So, instead of directly using the coal, you try to make it the fuel in the powder form and try to use them properly. So, basically from the plenum chamber you introduce the coal in a pulverized form, and into the combustion chamber, and in this combustion chamber there are submerged water tubes, and they get heat from these things. So, that means one side we get coal, other and air mixture that comes in, and this gets heated, and subsequently the water goes out, and the exhaust product, that means whatever left out, which is called as a flue gas, enters through the cyclone separator. So, this is how it operates, but it through this process what has is observed is that the as compared to conventional ones, the volumetric heat release increases about 10 to 15 times. So, that way we can say heat transfer rates, surface heat transfer rates also becomes higher from the conventional boiler. The next category of tube, and which is mainly what we are talking about, the steam generator, they fall under the category of water tube boilers, and in fact this water tube boilers or other way we call it as a steam generator, they are eventually same, but what we see is that these they have the components, different components like integration of economizers, boiler, superheater, reheater and air preheater. So, all these things are integrated in a sequence manner, so that a single entity, and that we normally call as steam generator, supplies the necessary quantity. So, water from high pressure feed water heater, which is about 230 to 260 degrees centigrade, that is received by an economizer and leaves saturated or two phase at low quality, then it enters the steam drum at a midpoint. So, more close look of this we can see here is that in the same figure what we see that when the water enters into the steam drum, when the from the economizer component, and when it enters, it is the basically collection or we can say reservoir for water, and to get saturated steam, one way is that we have to keep the water, take out of the water from the drum through the downcomer, and header is the meeting point between the heat source and this incoming water through the downcomer. When heat is being received, the steam gets generated. It since its density is low, it rises through an riser, and once we riser we get a superheated steam here, then subsequently saturated steam at this exit of the steam drum, and they are subsequently used for the superheater. So, essentially we are coming from this path, okay, and if there are some reheating is required, then we have a reheater unit. Reheating unit, that means once you have reached superheated steam and then first expansion takes place in the turbine, then you are reheating from 2 to 3. So, that reheating things comes from the reheating reheater, and again it is also part of the complete component of steam generator. Then through this process to operate this steam, we also require forced draft fans. So, forced draft fans that is mainly required to because we require very high steam rate. So, for that regions and mixing has to take place, and we also expect a temperature of close to 1650 degrees centigrade. So, that is the reason we also require forced draft fans. Again the combusted gas, they have to leave. So, once the combustion process is over, that exhaust from the steam has to leave from the stack through the fuel stack, and that leaving takes place through the at around 320 degrees centigrade. So, that is the reason we also require the induced draft fans that draws away, that means unwanted flue gases has to be drawn away from the systems, and then they have to get it outside of the stack, and moreover it has to go to the higher atmosphere or higher altitude, so that at a relatively higher height. So, that is the reason we require an induced draft fan. And of course, another category is that when we take this the water that comes out from the water, exit temperature is of the flue gas is about 150 degree centigrade, and this is also required. That is because there are many regions that why we require exit temperature more than 100 degree centigrade, just to make sure that we are exiting only the steam, I mean there is no component of water that remains in the entire unit, because it corrodes this surface due to condensation. Second thing is that when you go for higher temperatures, the flue gas has enough density becomes lower, so that they can go relatively to a larger height through this high plume. So, this makes through complete dispersion in the atmosphere. So, these are some constraints that we require that this to be attended while designing these water tube boilers. Then next segment that we are going to talk about one particular component of this water steam generator, that is steam drum. So, once you have this, we when you talk about steam drum, we say that it gives only saturated steam, but how does it happen? So, why I mean what are the different other complications that arises here? So, if you look at closely only for the steam drum, this is a particular figure which says that the drum essentially contains water, flour and the saturated steam, which is a mixture of this. We expect that the only saturated steam goes out as a steam inlet, and we also expect that only water goes through the downcomers, and the after receiving the heat from the fuel air, the steam has to rise, and when it rises, it also submerges in this water, and finally it goes as a saturated steam. So, so that means that we need to separate the saturated steam with respect to water. So, this is the first task that the steam drum does. And typically the size of the steam drum is about length, they are in the cylindrical configurations of a length of 30 meters and diameter of 5 meters, and a typical power plant must have at least 30 outlets, nozzles and many more downcomers and risers. And while taking the entry for water into the steam drum comes from the economizer unit, that means from the entry comes from the economizer unit. So, economizer is located somewhere here. Then there are possible ways that one of the important work that steam drum has to do is to separate the steam from the water. So, there are three classical mechanisms. One is gravity separation, second one is mechanical separation, third one is centrifugal separation. So, first category is most conveniently used, that is the gravity separation. That means it is basically density difference of steam and water. So, the gravity separation, taking the advantage of gravity separations, what we can see is that when the water velocity is low, then you can use this concept more easily, because the water velocities are low, and naturally the without any interference of water droplets, we can separate the steam and water. So, it is more economical for low steam quality and low pressure requirement. Now, when you go for relatively higher pressures, so we expect that the formation of water bubbles, because and that has to be, and that formation of water bubbles limits the steam production rate at the outlet. That means there may be possibility of since water bubbles also creates the choking of the steam outlet. So, for that reasons that water bubbles has been separated. So, that is what the mechanical arrangements like baffles, screens are made, so that separates it out, and that is relatively at higher pressures. Now, for very high pressures nearing to critical pressures, that means when we are mainly particularly when you are using one screw boiler, we expect that the steam production has to be continuous and at higher rate, because we are operating at very high pressures, and to do that we have to forcibly allow this water saturated steam to get out of the steam drum. So, for that we have the centrifugal separators devices, and there are incorporated, and finally also screens are also used in the drum exit for the final drying action. So, this is all about how the steam drum operates, different mechanisms. Now, we will again talk about very specific components, like in the steam drum we have used the word riser and downcomers. Downcomer is for water to come out from the steam drum, riser is for steam that goes up into the steam drum. So, if you take one particular segment, it is represented in this figure. So, we have a steam drum, the downcomer, the water comes in, and this height of this thing is what we call as H, and this through this downcomer, and subsequently water gets heat from the fossil fuel, and again it rises and enters into the steam drums. So, this process we call this as a natural circulation process. Now, we need to understand in a conventional natural circulation processes what is the mechanism, means how these density variations will help us in circulating water. So, mostly this is a very well standard concept that is used in the power plants. We will not cover about this only because this is a gravity circulations. Other two components will not cover in this section. So, like centrifugal separators or centrifugal devices or mechanical devices, baffles, screens, we will not cover to them in a deep manner. So, we will only talk about the natural circulation of water in a steam drum through the riser and downcomer arrangement. So, essentially the density difference is the driving force. We will try to find out what is the pressure requirement or what is pumping power requirement, that essentially depends on the pressure rise through this riser. To calculate this, what we have considered is that their possible ways of water circulations normally is favored for subcritical range of 160 bar, and when the critical pressure is above 221 bar, then density drops drastically. So, that means at critical point, if you look at the critical point of water, then at the critical point the difference in the density of water or steam is almost nil, negligible. So, that is the reason, that is the things that at very high pressure the difference between the steam and water densities decreases rapidly. So, this is although this is a very advantage part, also there is also disadvantage part, that natural circulation may not be a feasible options when you go for very high pressure operations. But however, let us assume that we are going for a natural circulation based water circulation through natural or buoyancy dependent water circulation. So, for that reason the critical parameter that we see out of this is that here when water comes through downcomer, its thermodynamic state is pure liquid, and when it enters to the riser, it is state in the heat gets added into this water and it becomes steam. So, essentially when the slug of mass is moving through risers, not all of the all the quantities of water become steam immediately. So, basically if whatever portion is there in the riser, slug of mass within the riser, it is a mixture of water and steam. So, that is a two phase systems. So, when it is a two phase system, so obviously there is a density difference. Now, we need to find out what is the average steam density of the mixtures. Now, to find this average steam density of the mixtures, we introduced the term which is called as a void fraction, another term which is alpha. Then we also talk about average density of the steam mixture in the riser part is this, and also average mixture density distributions, that is based on the amount of density with respect to liquid phase and density with respect to gas phase, and alpha separates out between these two, whereas alpha is nothing but the void fractions. So, a mathematical way of representation, I mean I am not going into deep into detail. First thing is that driving pressure you need to calculate through the density difference in the downcomer. So, in the downcomer what is the density and average density of this in the riser. So, that density difference into multiply by height is your power requirement. Now, to find this average density of water vapor mixture in the risers, this equation we are going to use, and this is nothing but the integration of mean average density over the entire height of the riser. So, that can be found out average density. A most standard way of expressions which you can directly take it from the books, it was like we can take the average, I mean it is well established expressions, what we call as rho r bar, which is nothing but average density of steam water mixture in the riser. You can use these particular expressions, and it was a empirical, or we can say it is a derived expressions which is mostly used in the steam power plant. So, using this we can find out this, and finally ultimately we can get the what is the driving pressure that is caused by the natural circulations. Of course, here there are other parameters that is involved. I mentioned one thing is the void fractions, which is defined as the ratio of volume of the vapor to the volume of steam water mixtures. Dryness factor is also important, which is referred as the mass of dry vapor of the steam to the combined mass of the steam and liquid in the mixture. Now, for a two phase systems, we also define a parameter which is called as a slip ratio. Since it is a two phase systems, we say that maybe vapor moves at a faster rate. So, how much faster, that typical value depends on the length path of the riser, that is h, and it is mainly in the range of 1 to 2, but we cannot go beyond 10. So, 1 to 2 is a reasonable number for water circulation in the boiler. Okay. Next part I have already mentioned several times, that once through boiler. So, once through boiler takes care about the operating the steam boiler at a conditions which is above the critical pressure 22 megapascals. So, through that, while operating at this pressure, it is possible to bring water to steam directly, bypassing its critical point. So, basically if you make a comparison of advantage of once through boiler and the conventional drum type boiler, this is shown in the figure. If you see the drum type steam generator, they have component like superheater, economizer or riser, downcomer. So, all these components are integral part of this. But when you see once through boiler, from the economizer to superheater, steam goes, water goes directly to steam. So, essentially that means we have to and for this to operate, we have to go for the pressure which is above than 22 megapascal for water. Although it is very lucrative options, lucrative options has many meaning, that means we are actually bypassing many important components like downcomer, riser, avoiding the heating part of liquid to vapor, that is transition state. So, all these things when we are bypassing, so this becomes an added advantage. But what another significant way in terms of economics is that if you look at the steam production, like throttled steam pressure and change in the heat rate. So, if you look at this part, then interestingly we can observe most important concept, that we can basically heat rate, if you say that it is defined as the amount of energy which is added to by heat transfer to a cycle to produce 1 unit of work output. Now, this heat rate comes down. So, if you see from this particular figure, one side we have throttle steam pressure which is the requirement, and heat rate comes down. That means, if you are increasing the throttle steam pressure and heat rate comes down, that means, the rate of heat addition in a one through boiler as compared to conventional boiler is heat rate is less. So, when the heat rate is less, that means, we are actually using with low quantity of fossil fuels, we can produce at higher steam. So, that is the advantage that economically one through boilers is chosen for many studies, many applications. Of course, for that when you talk about this one through boiler, we must have operating range of 130 to 276 bar, and its flow rate, and it has a flexibility of choosing the steam flow from very low to very high, from 4 to 1250 kg per second. So, that is the unanimous choice that one through boiler has many more advantage than the conventional water based boiler. And of course, one through boiler is most unanimous choice when you mainly goes for nuclear or any geothermal power plant systems, because of its uniqueness. That means, we can directly go from water to steam by bypassing the critical point. So, this is all about the overall steam generator and its applications. And before we end this lecture, let us solve some numerical problems based on our discussion so far. So, the problem statement goes like this: we have a steam generator, it burns a fuel oil with 20% excess air. The flue gas pressures leaving the air preheater is 3.1 bar, and we need to find out what is the minimum stack requirement to avoid the condensations. So, first thing is that let us understand that where is this air preheater is located. So, air preheater is somewhere here, and this air preheater is used to take heat from the flue gas, which is relatively goes out these things, and this flue gas is going as 3.1 bar. Now, when you call this 3.1 bar flue gas is going out, the flue gas components is essentially the products of combustion. So, main important requirement is that we must keep this stack temperature to a point or to a value for which there will not be any condensations. And why the condensation? Because the product of combustion mainly consist of water component H2O. Now, let us see how you go about it. So, first thing is that let us see that what is your the fuel. So, fuel in this case is the fuel oil. So, fuel oil, which is typically a fossil fuel. So, fossil fuel, and if you chemical formula, if you can just assume it is a kind of C12H26. So, this is the fuel oil, and you take this chemical composition as C12H26. So, for this the takes with air and it gives flue gas, and this flue gas mainly contains water. So, we need to find out, and this flue gas is leaving at 3.1 bar, and we need to find out that at this pressure the water should not condensate. So, you for this corresponding, but then to do that, for condensation of water, we also need to find out what is the partial pressure of this water vapors. To solve these problems, first thing that you need to understand, you have to find out stoichiometric combustion equation. Which says that any hydrocarbon CXHY, when it mixes with air, air means it contains oxygen plus 3.72 times nitrogen. So, basically mixture of nitrogen and oxygen with, suppose if you take 1 mole of oxygen, there has to be 3.72 moles of nitrogen, and when this combustion takes place, it gives X times CO2. A balanced chemical equation will look like this: Y by 2 H2O plus 3.76 A N2. Now, here A is equal to X plus Y by 4, and X and Y is nothing but the carbon and hydrogen. Now, if you take this, if you, in our case we have X is equal to 12, Y is equal to 26. So, this will imply A is equal to 18.5. Now, when you put all of them, the combustion equation will look like C12H26 plus 18.5 O2 plus 69.56 N2 gives rise to 12 CO2 plus 13 H2O plus 69.56 N2. But this is the stoichiometric combinations. But what happens? It actually burns with 20% excess air. That means, this number has to be increased by 20%. Now, when we increase by 20%, then new equation will come back. That means, 20% excess air. So, our combustion equation will be C12 plus C12H26 plus 22.2 O2. So, this also will be increased by 20%. So, this becomes 83.473 N2. So, this gives 12 CO2 remains as it is, H2O also will remain as it is. What will be there? Another 20% increase, that is 3.7 times O2 will be there. So, 20% of 3.7 will come, because 18.5 multiplied by 0.2 is nothing but your 3.7 O2, and then we will also have N2. So, this will be 83.473 473 N2. So, this is the combination of this. Now, once this is your balance equations, then we will be finding out what is the mole fraction of water. So, if I say this is YH2O, that is mole fraction of water, is nothing but 13, which is the number of moles of water. Total mole will be 12 plus 13 plus 3.7 plus 83.472. So, once we have mole fraction of water, so this number is 0.116. So, mole fraction of water, why do we require calculate? Because correspondingly we need to find out partial pressure. Of H2O. So, that is nothing but P H2O will be Y H2O multiplied by P total. Now, P total pressure you have given 3.81 bar. So, this number will be 0.116 into 3.1. So, that means P H2O is 0.3596 bar. So, that means, we need to have the saturation pressure at will be 3.96 bar, but our question is asking for temperatures. So, we refer steam table that involves for saturated water pressures. So, this will give you means we have to use saturated pressure table. So, this will give you TH2O corresponding to this saturation pressure is approximately 72 degree centigrades. So, this is your answer. We say that we have to minimum temperature of the stack temperature should be 72 degree centigrades to avoid condensations, and essentially this is the requirement ki condensation should not happen because it will have a corrosion effect. So, the next important problem that we will talk about is about the natural circulation in the water tube boiler. So, I have mentioned several times that we are going for the calculate the driving pressure delta P d, which is the density difference between the downcomer and riser consists of combination of steam and water. So, we need to find out the average density distributions through these expressions, and in these expressions the terms like we are using xi alpha, which is the void fractions, xi is the another fixed term, I will explain that is the ratio of specific volumes. So, to solve these problems, let us, and also we know this exit quality. So, for these solutions is a very simple with a viewpoint that we must understand ki what are these notations that we have to calculate individually. So, first thing is height is h, which is given as 12 meter, that is riser height. Xg, that means exit quality of the steam at this point is 50%, that is 0.5, and it operates at 170 bar, so 172 bar. So, P is equal to 172 bar. Now, here when it is operating in liquid plus vapor mixture. So, from the steam table you refer saturated vapor conditions. So, this will give you two important parameters at this pressure at 172 bar. We can find out what is Vf is 0.00177 meter cube per kg, and Vg is equal to 0.00836 meter cube per kg, and here the equation requires density. We find rho f, that is inverse of Vf, and this is 565 kg per meter cube, and rho g is equal to 119.6 kg per meter cube. Then first term we have to find out what is void fraction. Void fraction, which is alpha e. You recall our expression, that is 1 by 1 plus 1 minus x by xc. Xc is your exit quality of the steam into xi. And what is xi? Xi is nothing but Vf by Vg into S. S is nothing but your slip ratio. I mentioned since the steam in this riser, it is a mixture of liquid vapor mixtures. So, vapor travels at a faster rate. So, that means we say that for this slip ratio is about 1.2 times higher. So, this for this factor xi is represented here. Now, we taking this as 1.2 and we know Vf and Vg. So, xi number is 0.254, and when you have xi is 0.254, xc is 0.5. So, this will give alpha e. When you insert this value, we get alpha e is equal to 0.8. Now, when you have all this number, then we can find out what is rho r bar, that is average density of steam water mixture in the risers. So, you have rho f, rho g already known here, xi already we have calculated, then alpha e the void fractions already calculated, and putting this, inserting this value in this conventional expressions, we find what is rho e bar is 331 kg per meter cube. Now, once you know this rho bar, then we can calculate delta P d for the downcomer. It is nothing but rho downcomer minus rho r bar. So, downcomer density is mainly liquid, that is 565. So, this number can be assumed as this 565. So, delta P d can be calculated as 565 minus 331. So, this part is done. G is 9.81 meter per second square. H is the height of the riser, that is 12 meter. Now, putting this, your delta P d is calculated as 27546 Newton per meter square, and delta P d is approximately 0.275 bar. So, driving pressure for this system through this circulation is about 0.275 bar. So, that means we need to give some additional device that can create this pressure, so that the steam can rise in the riser. So, this is all about the discussion today. Thank you for your attention.